And a probability histogram is just like a relative frequency histogram. The only difference is that the vertical scale shows probabilities instead of relative frequencies, but they're basically the same thing. So for a discrete probability distribution, we usually use 1 bar for each value of x, or 1 bar for each outcome. Let's look at probability histograms for some of the experiments we've already talked about. Selecting a part and inspecting it if 8% of the parts are defective. Here was our probability distribution, and this would be our probability histogram. We have our two outcomes, 0 and 1. Each one gets 1 bar, and the probability for the 0 was 0.92. The probability for the 1 was 0.08. For rolling a die, we had these 6 possible outcomes, and each one had a probability of 1/6. So in this one, every outcome has the same probability value, so this goes straight across on the top. Each one of these outcomes has a probability of 1/6. So the mean of a discrete random variable is given by this formula, where x is the value of the random variable and p of x is the probability of observing the value x. So what this formula tells you to do is for each value of x to multiply the value times its probability and then add up those results, and that gives you the mean. And again here, the mean actually represents the center of the data. If we think about our probability distribution as being sort of like a frequency distribution, we can look at our probability histogram and make an estimate as to where the center of this data would be, or where the mean would be. In this case, our highest value was for 10, and so we could make an estimate that the mean of this distribution would be somewhere around 10. Now, the big question with the mean for a probability distribution is, how do we interpret it? So the mean of a random variable represents the mean of the outcomes of the experiment in the long run. If the experiment is repeated as the number of trials increases, the mean of the actual outcomes gets closer to the mean of the random variable. So the mean of the random variable is also called the expected value, because it is what we would expect to happen in the long run, and it's sometimes denoted by a capital E of x. Here's an example for expected value. The probability distribution that we already looked at for the number of DVDs a person rents from a video store during a single visit had a mean of 1.49. So let's interpret this as the expected value of our random variable x. Our expected value is the same as the mean, which was 1.49. So to interpret this, we'd say consider each customer's visit as one trial of this experiment. In the long run, the average number of DVDs rented by customers during a single visit is 1.49. Now, we're not going to have any one customer come in and rent 1.49 videos, obviously. But what this tells us is that for most customers who come in, they're either going to rent 1 or 2 videos, so that the average is going to come out to be about 1.5. Now, if you're the store owner and you're wondering how many videos you're going to be renting out during a certain number of customer visits, you can use this expected value to help you with that. For example, in 1,000 customer visits, the total number of DVD rentals we would expect is 1,000 times 1.49, or 1,490. In other words, again, the average number of DVDs rented by a customer during a single visit is 1.49. So if we take that average times the total number of customer visits, we get an estimate of the total number of DVD rentals we would expect in those 1,000 visits.